The James Webb Space Telescope, or JWST, is the largest and most powerful space telescope ever built. Launched on December 25, 2021, it operates at the second Sun-Earth Lagrange point. JWST is a collaborative project by NASA, the European Space Agency, and the Canadian Space Agency, providing an overview of its mission, history, design, instruments, and scientific results. The origins of JWST trace back to the 1980s with discussions about a successor to the Hubble Space Telescope. In 1996, the HST and Beyond Committee recommended a large infrared space telescope. The project was initially called the Next Generation Space Telescope before being renamed in 2002 after former NASA Administrator James E. Webb. JWST launched on December 25, 2021. JWST was designed to be a large infrared telescope with a 6.5-meter primary mirror, compared to Hubble's 2.4-meter mirror. To achieve the required sensitivity, the telescope and instruments need to be kept extremely cold, below 50 Kelvin. This is accomplished by positioning JWST at the L2 Lagrange point, about 1.5 million kilometers from Earth, and using a large sunshield to block heat and light from the Sun, Earth, and Moon. The optical telescope element of JWST consists of a primary mirror made up of 18 hexagonal beryllium mirror segments, a convex secondary mirror, and an aft optical assembly subsystem containing a tertiary mirror and a fine steering mirror. All mirrors are coated with gold. The total collecting area of the primary mirror is 25.4 square meters, as measured on orbit using the NIR-CAM pupil imaging lens. The spacecraft provides power, pointing, orbit maintenance, data storage, and communications for the observatory. The solar array provides an average of 1.5 kilowatts of power, and the pointing system uses star trackers and inertial reference units to point the telescope. Communications are handled through the Deep Space Network. The sunshield consists of 5 layers of Kapton, about 14 meters by 22 meters in size, that separate the spacecraft from the telescope and attenuate the incident solar radiation to milliwatt levels. The sunshield size and geometry provide an instantaneous field of regard of 40% of the sky in an annulus that sweeps around the full sky once per year. JWST has 4 main science instruments: NIR-CAM, Near-Infrared Camera, NIRSpec, Near-Infrared Spectrograph, MIRI, Mid-Infrared Instrument, and NIRICE, Near-Infrared Imager and Slitless Spectrograph. Each instrument is designed to capture different aspects of the universe in infrared light. NIR-CAM provides imaging from 0.6 micrometers to 5.0 micrometers in broadband, medium band, and narrowband filters. It has a wide-field slitless spectroscopy capability from 2.5 micrometers to 5.0 micrometers and is designed with 2 modules for observing parallel fields of view. NIR-CAM contains 2 extra-wide filters, 8 broadband filters, 12 medium-band filters, and 7 narrowband filters. The broadband filters span the full wavelength range of the instrument, and the narrowband filters are matched to individual spectral lines. NIR-CAM imaging sensitivity exceeds pre-launch expectations in almost all filters. NIR-CAM wide-field slitless spectroscopy provides 1,600 spectra of all objects within the field of view using a grism. This mode is used in the long wavelength channel in combination with a wide or medium filter to provide spectroscopy in the 2.5 micrometers to 5.0 micrometers wavelength range. NIR-CAM coronagraphy has 3 round and 2 bar-shaped coronagraphic masks for occulting a bright object. The inner working angles range from 0.4000 to 0.8800 for the bar masks. During a bar observation, the bright object is positioned behind the bar at the location where the EWA is smallest. This mode provided a 5 sigma contrast at 100 better than 4 × 10⁻⁵. Bright object time series observations are designed to measure photometric variations in relatively bright sources. NIR-CAM imaging bots uses rapid readout of subarrays to increase the readout cadence and increase the saturation limits. NIR-CAM grism bots provides 1,600 spectroscopic observations of bright, isolated, time-varying sources. NIRSpec provides spectroscopy from 0.6 micrometers to 5.3 micrometers at various resolutions. The detector system consists of 2 Teledyne 2048x2048 H2RG arrays controlled and read by sidecar ASICs. The detector arrays project to an average of 0.10300 in the dispersion direction and 0.10500 in the spatial direction. NIRSpec multi-object spectroscopy is done using the MSA, which is a MEMS assembly consisting of 4 quadrants. Each MSA slit is configurable to observe up to 100 objects simultaneously, including sky subtraction, without overlapping spectra. NIRSpec has 5 fixed slits, which provide the highest contrast and throughput on individual targets for the highest spectral resolution. The fixed slits are used primarily with the NIRSpec Bright Object Time Series mode. The IFU entrance aperture is a contiguous 3.1 times 3.2 field of view, divided into 30 slices totaling 900 spaxels. By providing a full spectral data cube, the mode gives the most complete information on a single target in the near-infrared with JWST. NIRSpec BOTS primarily uses the 1.6 times 1.6 fixed slit, combined with detector subarrays to observe bright time-varying objects such as stars with transiting exoplanets. The mode can be as fast as 0.28 s, potentially reaching stars brighter than J6 in some modes. NIRSpec provides 3 specialized scientific capabilities and redundant backup to NIRCAM over the wavelength range 0.7 micrometers to 5.0 micrometers. NIRSpec is packaged with the FGS, which has a separate field of view of 2.2 times 2.2, matching the FOV of one of the 2 NIRCAM channels. NIRSpec single object slitless spectroscopy defocuses the telescope beam to spread the signal from bright objects over about 25 pixels to avoid saturation. SOS provides medium resolution spectroscopy between 0.6 micrometers and 2.8 micrometers. NIRSpec wide field slitless spectroscopy enables low resolution spectroscopy over the 2.2 times 2.2 FOV at 0.8 micrometers to 2.2 micrometers wavelength. It is optimized to search for Li alpha emitting galaxies during the epoch of ionization and can be used efficiently in parallel mode. NIRSpec aperture masking interferometry, or AMI, uses a 7 aperture mask to enable high contrast imaging at an inner working angle less than λ/d. AMI is used with the f380M, f430M, or f480M filters, and typically uses an 80 x 80 pixel subarray for bright sources. During commissioning, AMI was demonstrated by detecting Abdor-C, a companion separated by 0.3 with a contrast ratio of 4.5 mag. NIRSpec includes an imaging capability using a set of backup NIRCAM broadband filters and some medium band filters. As NIRSpec imaging covers half the FOV of NIRCAM, and does not include a dichroic, this mode is primarily for imaging redundancy in the mission. NIRSpec imaging can also be used in parallel to NIRCAM imaging for additional aerial coverage, and is used in support of WFSS data. MIRI, or mid-infrared instrument, provides both imaging and broadband filters and IFU spectroscopy from 5.0 micrometers to 28.0 micrometers. It also has low-resolution slit spectroscopy from 5.0 micrometers to 12.0 micrometers, where the sensitivity is limited by the zodiacal light background, and a coronagraphic capability. MIRI has 3 arsenic-doped silicon (CAS) impurity band conduction detector arrays, each of 1024 x 1024 pixel format with 25 micrometers pixel pitch. The plate scale is 110 milliarsec per pixel, which Nyquist samples the point spread function at 6.25 micrometers. MIRI imaging uses 9 broadband filters to cover the 5 micrometers to 27 micrometers wavelength region. The imaging field of view is 1.4 times 1.9 Arcman 2 sampled with 0.11 pixels. The remaining field of view of the detector is occupied by the coronagraphs and the low-resolution spectrometer. MIRI imaging can use subarray readouts for bright objects that would saturate in a full frame, observing objects as bright as 0.1 G in the F560W filter. MIRI low-resolution spectroscopy, or LRS, provides our 100 long slit and slitless spectroscopy from 5 micrometers to 12 micrometers, the mere wavelength range where JWST observations are still zodiacal light limited. A slit mask is permanently in the field of view. Slitless spectroscopy is available anywhere within the imager field of view when the R100 double prism assembly is selected in the imaging filter wheel. For bright sources, a subarray readout can be used. MIRI medium resolution spectroscopy, or MISS, provides integral field spectroscopy over the full 5 micrometers to 28 micrometers MIRI wavelength range. The spectral resolution ranges from 3300 at the short wavelength end to 1300 at the longest wavelengths. There are 4 channels separated in wavelength by dichroics, with between 12 and 21 image slices. Depending on wavelength, the field of view ranges from 3.7 times 3.7 to 7.7 times 7.7. Each individual exposure provides 2 wavelength ranges on 2 detectors. 3 exposures are required to get a full wavelength spectrum. The imaging channel on MIRI includes 4 coronagraphs for high contrast imaging. The 4 coronagraphs are for observations at 10.65 micrometers, 11.40 micrometers, 15.50 micrometers and 23 micrometers. The short wavelength coronagraphs use 4-quadrant phase masks, 4 QPM, while the other is a more traditional LIOT design with an occulting spot and a pupil plane stop. The 4 QPMs are usable at a smaller inner working angle than the LIOT mask, and can be used at each field of view, FOV, in the imaging channel. Each of the 4 QPMs provides a field of 24 x 24, while the LIOT spot mask provides a 30 x 30 field. Each of the coronagraphs demonstrated a high contrast ratio 10,000:1 from the star during commissioning. JWST is controlled from a Mission Operations Center, MOC, at the Space Telescope Science Institute, STI, which also runs the JWST science program. STI issues annual calls for proposals, CFPs, for the General Observer programs. In between the CFPs, proposals for time-critical observations, or other observations that cannot be proposed to the annual call are considered for the director's discretionary time. The scope of JWST's competitively selected programs range from large and treasury programs that address multiple science goals and produce multi-use datasets to small programs that target important but specific science goals. All of the JWST data taken, including science programs and calibration data, are placed in the Mikulski Archive for Space Telescopes, MAST, at STI and made available to the original proposers within a day or two of the data being taken. After an exclusive use period that ranges from 0 to 12 months depending on the type of program, the data are also freely available to other astronomers for archival research and other purposes. JWST data analysis tools are provided through the JWST user documentation, docs. JWST has already begun to address questions in its 4 key science themes: first galaxies, star formation, galaxy assembly, and exoplanets. It has measured spectroscopic redshifts of galaxies beyond Z equals 13, studied interactions between massive stars and surrounding material, detected galaxy bars at Z greater than 1 and examined quasar-galaxy connection at Z equals 2.94, and measured temperature of a rocky exoplanet, finding detection of CO2 in an exoplanet atmosphere. Further JWST observations will continue to address the original science themes, and it is likely that the universe will surprise us with unexpected discoveries.